In 1916, a single winter storm flooded 27,000 acres of the Netherlands and killed dozens in their sleep. The Zuiderzee, an inland arm of the North Sea, had no barrier and no lock system capable of holding back a surge. Engineers proposed sealing the entire sea with a 20-mile dam built on sand that shifted with every tide. Critics called it a monument to ambition that physics would never allow. The Zuiderzee had been expanding for centuries. Medieval storms breached coastal dunes and turned a shallow freshwater lake into a tidal basin connected directly to the ocean. By the early 20th century, saltwater intrusion threatened farmland. Fishing villages relied on shrinking catches, and coastal provinces faced chronic flooding. Cornelis Lely, a civil engineer and politician, proposed a solution in 1891. Close the Zuiderzee with a dam, pump out the enclosed water, and reclaim the seabed as farmland. The plan required building a continuous barrier across open water where the bottom was soft clay, currents reversed twice daily, and winter ice could shear through anything anchored to the bed. Parliament authorized the project in 1918, 2 years after the flood that killed 77 people. The dam, named the Afsluitdijk, would run from the province of North Holland to Friesland, cutting the Zuiderzee off from the Wadden Sea and the ocean beyond. Once closed, engineers could lower the water level inside, flush out the salt with river discharge, and convert the basin into a controlled freshwater lake. The difficulty was not the concept, it was the fact that conventional cofferdam methods required stable ground, and the Zuiderzee floor was anything but stable. Pilings driven into the clay bent under lateral pressure. Temporary berms built to redirect currents washed away before the next barge arrived. Early feasibility studies concluded that any attempt to close the gap in a single season would require more material than the national rail network could transport. Construction began in 1927. Engineers built the dam from both shores simultaneously, advancing toward a central gap where tidal currents reached their highest velocity. They used boulder clay dredged from the seabed and glacial till transported by barge, dumping material in layers and compacting it with steamrollers. The dam cross-section was trapezoidal, narrow at the crest and wide at the base to resist wave pressure and horizontal loads from the tides. Workers laid willow mattresses on the seafloor first, weighted with stone, to create a permeable foundation that allowed water to pass through while holding the clay in place. Above the mattresses, they built up the core with successive lifts of clay, each layer sealed and compacted before the next was placed. The outer slopes were armored with basalt blocks imported from quarries in Germany and Scandinavia, sized large enough that wave action could not displace them. As the two sections extended toward each other, the gap funneled increasing volumes of water through a shrinking opening. Current speed doubled, then tripled. The final closure required blocking a channel where water moved fast enough to erode dumped stone faster than barges could replace it. Engineers calculated that if the gap fell below 400 meters, tidal velocity would exceed 4 meters per second, fast enough to scour the bed down to bedrock and destabilize both advancing sections of the dam. Weather added another variable. Work could only proceed during neap tides, when the difference between high and low water was smallest, and only in conditions calm enough for barges to hold position. A single winter storm could undo weeks of progress. The turning point came in the spring of 1932. Engineers abandoned the symmetrical closure plan and shifted to an asymmetric strategy. Instead of meeting in the middle, they extended one arm of the dam farther than the other, forcing the tidal current to flow around a longer path. This reduced the velocity in the remaining gap just enough to allow stone and clay to settle before the next tide displaced it. The final approach used a technique adapted from river engineering. Instead of dumping material vertically into the current, barges released loads upstream and let the flow carry them into position. The current itself became the placement mechanism. On May 28, 1932, workers closed the final gap with a combination of willow mattresses, sandbags, and clay. The Zuiderzee became the Meer, a freshwater lake isolated from the sea. The dam itself is 32 kilometers long and 90 meters wide at the base. The crest rises 7.5 meters above sea level and supports a 2-lane highway that opened to traffic in 1933. At the midpoint and at both ends, the dam contains discharge sluices that release excess river water into the Wadden Sea when the lake level rises. The sluices are gravity-operated, meaning they open automatically when the difference in water height between the lake and the sea exceeds a set threshold. This passive system prevented the Meer from overfilling during wet seasons without requiring pumps or manual intervention. Each sluice complex contains multiple gates, sized to handle the combined discharge of the River and its tributaries during spring floods. The gates were designed to operate under a head difference of up to 2 meters, enough to drain peak flow without overtopping the dam. The economic justification for the dam was land reclamation. Once the Zuiderzee was closed, engineers built secondary dikes within the Meer, subdividing it into smaller sections called polders. Pumps removed the water, exposing the clay lakebed, which was then drained, desalinated, and converted to farmland. The Noordoostpolder was completed in 1942, adding 460 square kilometers of new land. Eastern Flevoland followed in 1957, and Southern Flevoland in 1968. Together, the reclaimed polders form the province of Flevoland, established in 1986 as the 12th and newest province of the Netherlands. At just over 1,400 square kilometers of dry land, Flevoland is the smallest province by area, but it contains some of the most productive agricultural soil in Europe. The clay that spent centuries underwater, insulated from oxidation and leaching, retained mineral content and organic matter that made it immediately suitable for intensive farming. The total cost of the Zuiderzee works, including the Afsluitdijk and all polders, exceeded 5 billion guilders in period currency. Closing the sea had consequences that models did not predict. The Meer is fed by the River and several smaller tributaries, all of which carry sediment. Without tidal flushing, silt accumulated on the lakebed, reducing depth and storage capacity. Ecologists documented the collapse of saltwater species and the establishment of a freshwater ecosystem that favored different fish, birds, and plant communities. Coastal fishing villages that had relied on North Sea access lost their economic base and either converted to freshwater aquaculture or declined. Some experts argued the dam created as many problems as it solved, redistributing risk rather than eliminating it. The elimination of tidal exchange also concentrated nutrient runoff from agriculture, leading to seasonal algae blooms that required additional water management interventions. The Afsluitdijk remains in active use, but it no longer meets modern safety standards. In 2018, the Dutch government began a renovation program to raise the dam, reinforce the sluices, and add pumping capacity to handle increased river discharge driven by climate change. The work is scheduled for completion in 2028. Engineers are also installing tide-driven turbines in the sluice complexes to generate electricity from the water flowing between the lake and the sea, converting the hydraulic head into renewable power without altering the dam's flood control function. The renovation includes widening the highway to 4 lanes and replacing the original concrete surface, which has fractured under decades of freeze-thaw cycles and heavy truck traffic. The structural core of the dam, however, remains the same boulder clay and willow mattresses placed between 1927 and 1932, still stable nearly a century after closure. The Afsluitdijk demonstrated that closure of a tidal basin was structurally possible, but it did not prove that closure was without cost. The Netherlands gained 1,200 square kilometers of farmland and eliminated storm surge risk in the former Zuiderzee, but it also created a static lake that requires continuous management, periodic dredging, and infrastructure that must be upgraded every few decades to keep pace with subsidence and sea level rise. The dam bought time and space. It did not end the hydraulic problem. It reformulated the problem in terms that engineering could address one upgrade at a time. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.